Hello everyone. So today we will go through LLVM and its space within the FreeBSD ecosystem. So I'm David Carlier. I contribute to various open source projects, but more or less related to the BSD world. Can be video games, can be enterprise oriented software. More related to the topic of the day, I'm LLVM committer since May 2018. Okay. So, what is LLVM? LLVM is a compound of toolset and front ends. Front ends which are able to generate what we call LLVM IR. IR stands for intermediate representation. It's kind of high-level assembly, but much more architecture independent. So if we take as an example Clang or Clang++ front ends from your source code, the Lexer will generate symbols which will be sent to the SEMA to generate the AST, which is abstract syntax tree, and then to the code gen to generate the LLVM IR. So with LLVM, we have also tools. You can build nice just-in-time compilers. You can extend LLVM itself. For instance, you can make module, what we call module path, which is an extension on the compilation unit perspective, and then function path, basic block path, and so on. When you can do some commit checking, you can add some instruction, remove some instruction if you like. It's in the compilation times paths, right? You have, in addition, the possibility to do some static code analysis. We have what we call sanitizers. We go through later. All of this available in FreeBSD since 9.10-ish. First, it was just an option parallel to the old GCC 4.2. It was first a need to replace the old 4.2, which was the last GPL2 version. So it was quite a blocker, because from this you can do C++ 11 and so forth. You can do only C99. So it was time to replace this for the system. It took so then it became full part of the system since FreeBSD 10. I mean, it's used to build the kernel, the userland, most of the ports. So yes, the FreeBSD code base needs a lot of changes to fit Clang criteria. Hello. Yes, a lot of changes to fit more modern style and so on. So then as the time goes, more and more architecture was supported, AMD 64, ARM, and then maybe only SPARC 64 remains a bit behind the rest, but that's already a nice progress. So yes, here we go. So sanitizers, what are these? It's not really to clean up things, like the name might say. It's more to detect at runtime some type of bugs. So it's kind of, you complete pretty much well the static code analysis part. So sanitizer gives many different runtime library to detect some type of bug for memory, for rest condition, for several kinds of overflow. For instance, we have memory sanitizer. It's mainly about initialized variables. Address sanitizer, it's more for double free, IP stack overflow. Well, for only NetBSD have also, in addition, the leak sanitizer, which is pretty effective and also have much less performance drop compared to tools like Valgrind, for example, which can be 20 times slower, whereas with address sanitizer, it's 5 times slower sometimes. So yeah, it's pretty much. We have undefined behavior sanitizer. It's kind of small Swiss knife sanitizer. I mean, there is no shadow memory mapping, unlike address sanitizer or memory sanitizers. So it was, for instance, possible to port it to OpenBSD for this reason. It's kind of small sanitizer. It's only for integer overflow, misaligned pointers. And the performance drop is pretty small compared to that. You can combine it with other sanitizer, whereas memory sanitizer and address sanitizer, you can't use them at the same time. They are mutually exclusive. We have a nice rest condition detection called thread sanitizer. So all of them are supported by FreeBSD. In addition, we have components like Deep Fuzzer to do some fuzzing and X-ray instrumentation to do some performance benchmarking. Right? So for example, sorry. So, for example, this very basic code, address sanitizer is perfectly capable to catch the first error, the double free is perfectly capable to catch it. The use after free as well. As you can see, it detects the first heap overflow, as you can see. It displays a line here. Memory sanitizer as well is capable to catch this initialized variable, which can go under the radar very well in production. It works-ish in release and production environment, but it's not correct code, obviously. As well, thread sanitizer is perfectly capable to catch this obvious race condition, like this. Again, it shows you where the problem lies. Ah, sorry. Okay. So here, memory sanitizer was able to catch the initialized variable very well. Undefined behavior sanitizer is capable to catch those two obvious errors, the alignment issue and then the integer overflow just below. As you can see.
Interrupting you? Oh no. Okay, that's good.
So here, to show you the flag to pass to the front end. So memory sanitizer is memory, address sanitizer is address, thread sanitizer thread, and then undefined behavior. Right. So. So we mentioned earlier the leap fuzzer component. But what is fuzzing all about in the first place? Well, it's a testing technique to catch certain type of bugs with software, mainly libraries, I might say, which relies on external inputs. Can be just reading a config file, can be listening a socket, whatever you like. If we take an example, an image picture parser, if you want to fuzz the picture format detection, if you want to fuzz how it detects it's a PNG, JPEG, and so on. So the leap fuzzer will use inputs which we can call corpuses in the fuzzing vocabulary. So those corpuses don't have to be full pictures, can be just the first bytes of the picture format. Then the leap fuzzer will take those corpuses, will proceed to do some transformation which we call mutations. It will insert some random bytes to some random offset, remove some other bytes eventually, in order to trigger segmentation fault, bus error, whatever. Those mutations will be then stored, so they can be reused once you fix your bugs. So fuzzing is meant to be run long enough, I mean hours at least, if not days, if not weeks, if necessary, in order to cover the code as much as possible. So as you can see, that completes pretty well the unit test we all know. But leap fuzzing is nice, but there is some culprits. I mean, as I said, it fits better with library, because with monolithic applications, for instance, if you want to fuzz Nginx, that can become very difficult. It's software relying on events, and leap fuzzer runs the code several times. That can contradict pretty much the application workflow for this case. You might need to do a lot of code changes in order to fit leap fuzzer needs. So here, to display how leap fuzzer works, you have your first binary. You have one or several corpuses. We have also, as an option, it supports dictionary. Dictionary is a sort of way to guide the fuzzing. Sometimes you may want to avoid too much pointless randomness. Let's take as an example, you want to fuzz HTTP server, you might not want to fuzz keywords like get, put, delete, and so on, just maybe some part of the client request. So dictionary is a good way to guide a little bit, to make more sense of the fuzzing. And then with the corpus and then eventually the dictionary, the inputs will undergo some mutation. And those mutations will be then stored in the same place as the original inputs. So how in practice work a little further? You need to at least implement LLVM further test one input, which take as an argument the mutated data. So it's a C function, right? And then you do what you have to do with this. So for instance, there is an obvious overflow here. So that's why I recommend to combine further with at least a sanitizer, like address sanitizer, for instance. Once you compile your first binary, sorry, you will see. So I type this. And then it comes with several options. You can choose how much run it will do, the memory usage limit. If you want to do some parallel jobs, what you can do as well is the max length of inputs, the initial seed for randomness. There's plenty. Well, again, on FreeBSD, the leak detection is not supported, but there's many. So then you have to create a meaningful corpus folder.
Cannot see what you're typing.
Sorry. Yeah. For instance, I ask him to run 200 times with this inputs folder. And then it was able to catch the overflow. So it created a crash file. Okay, it was empty. again. So yeah, normally it should create some mutated data with an hash code and then the transform inputs. So. So, as you can see, okay, here it is. So we have now X-ray instrumentation. It's, as I said earlier, it's for doing performance benchmarking. Means, for example, you're doing just release a new version of your software for your company, and then a customer of yours calls you to tell you that this new release had a severe performance drops compared to the previous version. So X-ray instrumentation allows you, at least will help you to find out where the bottlenecks really lies. So X-ray instrumentation will, when you compile your binary with X-ray instrumentation, will put some instrumentation hook in each function entry and each function excite for the instrumented function, because you can choose which function you want to instrument and which function you don't want to. As for instance, the more function you instrument, the slower the binary will get. So you have to choose carefully which part of the code you want to instrument. In order to do this, you need to add those attributes. So you want to instrument always those two. You can also say you don't want to you have to write these attributes. To discard the function you want to avoid to instrument. So by default, once you run your updated binary, it will create a file, but you can change the file naming. It's by default, it's X-ray log, the name of the application, and then a hash, right? But then, with LLVM X-ray, you can find out you can do some accounting. That means showing where your application spends most of the time. You can order, because it will generate kind of CSV-like presentation. Then so it says here the first version of the Fibonacci function is the bottleneck in this case, right? So that's nice, adding some attributes, in practical, I might say you may not want to touch your code too much to that degree, at least when it's your corporate work. So fortunately, there is another solution. It's via an external configuration file, as follows. Can say, please always instrument those two, and you can say like this too. Never instrument this one, please. And then you can pass this config file as follows. Right? Same thing, it generates the same binary. So to summarize, here your binary compiled with extra instrumentation. So I mentioned instrumentation hook, but they are empty until you run the binary, and then it will fill with the timer. So in the beginning of each function, in the end, the excite point of each function, in order to generate the delta. So with LLVM X-ray graph, you can generate the code graph, and then from this you can generate SVG, for example. So extra instrumentation works well with multi-thread case, but you have the possibility to aggregate data because it can become very verbose, obviously. So you can tell to aggregate the data in one point. So yes. So yes, that will be all. Unfortunately, my FreeBSD machine had crashed yesterday, so I couldn't use it. If you have any concern, question,
So questions?